Yeah, I'm Duane Wessels from Verisign. I'm going to talk to you today about some of our observations from conducting DNSSEC algorithm rollovers to 3 TLDs. And I guess it doesn't say, but we're talking about COMNet and EDU for the record. Preparations for this started early in 2023. At that time, we were using RSA, algorithm 8, and we want to move to algorithm 13. There was extensive QA and OTE testing. The design is a fully hands-off design so that everything happens on an automated schedule at specific times. And just because I'm up here speaking to you today does not mean that I deserve really any of the credit for pulling this off. This was a huge effort within the company, many teams, 35 or more people, weekly meetings, something we obviously took very seriously. So they really get all the credit. I'm just here because I get to look at the traffic and see what sort of came out on the other side. So one of our big concerns with a KSK rollover and an algorithm rollover has to do with scheduling. You know, from our experience, or from what we can see, mostly all of the problems with these kind of rollovers happen because something happened out of order. A key was published at the wrong time or pulled at the wrong time. And so our solution to that was to do a lot of testing, use a conservative double signing approach, and as I said, everything is on an automated schedule. So those were well tested before we went into production. Our other main concern was about resolution failures from resolvers that are unable to query over TCP. We knew there was going to be an increase in packet size, truncation and all that. And our solution there was to do a lot of outreach to the community, coordinate with the large resolver operators. We did a lot of real-time monitoring. We were ready to do outreach if necessary. And as sort of a last resort, following up from the talk that Ralph and I gave about Akamai's domains, we had this option to tweak the truncation policy if necessary. But it turns out we did not need to do that. This was the schedule that we used for all 3 of the TLDs. You can see that it takes almost 2 weeks to go from start to finish. One of the reasons that it takes a little bit longer than you might expect is because of the way we manage our re-signing. Our TLDs are re-signed about 25% per day, so that takes 4 days to fully add all the new signatures of the new algorithm, and then similarly to remove the old algorithm from the zone at the end. All right, so let's take a look at traffic volumes. This was for .edu, which was the first TLD that we did. This graph may look familiar because it's similar to the one from the Akamai talk. The purple line at the top is the level of UDP query traffic. The green line is a subset of that UDP traffic, which is truncated, and then the blue line is TCP. And you can see at the start here, the UDP line is a little bit uneven. Those actually turned out to be some attacks that were happening at the time. Those were not related to the algorithm rollover, and they started before the algorithm rollover. They did give us a little bit of a scare, but those turned out to be DDoS attacks. But you can see that at the start, both TCP and truncation are very low, and they rise up, and then fall back down at the end. So that was EDU. This is net, and again, it looks very similar. The overall the UDP traffic is pretty flat. There is an increase in the middle, definitely an increase in truncation, increase in TCP, and then it goes back down. And COM is, again, very similar. So, what we really want to talk about, though, is response sizes, truncation, and TCP. A lot of us probably know this already, but the factors that affect truncation are the client's maximum UDP size, the server's maximum UDP size, so the minimum of those two, the number of records in a delegation, number of NS, DS, and glue records, and then the policy for truncation. And we are implementing or in compliance with RFC 9471, which has a pretty strict truncation policy. Thinking about the kind of queries we get and the kind of responses we return, they're broken down into these 5 categories here. And it shows how they're impacted by a double signing algorithm rollover. Oh my gosh, I'm not going to make 5 minutes. So the ones that we're most concerned about is the NX domain responses, because they already start out sort of large. They have 4 signatures. That adds 400 more bytes to the response, and all of those will exceed standard truncation limits and need to be retried over TCP. I've got a bunch of slides here, which I'm going to sort of go through fast because I don't have really enough time. But these histograms show for different types of responses their distributions, where they land in terms of sizes. So for example, these are responses without DNSSEC. They are not affected by the rollover. Secure referral responses, which is about 3.5% of our traffic, has a moderate increase because it's only 1 more signature. Insecure has 2 more signatures, slightly more increase, but again, well below most truncation limits. The ones, again, the NX domain is the one that's really of concern because it's already a large size, and during the double signing period, all the responses are above 1,500 bytes. So this is similar to the earlier graphs that shows that we got a lot higher levels of truncation than expected. As you can see, before the algorithm rollover starts, TCP and UDP truncation are essentially the same. You know, they're almost identical. But during the rollover, we see this divergence where we see a lot more TCP truncation compared to TCP, indicating a lot of resolvers are not falling back to TCP, it would seem, right? But so, you know, why so much? Obviously, because the responses got bigger, but is it because resolvers are unable to query over TCP? Is it because maybe there are some non-resolver clients that don't really need the full untruncated response, and they're satisfied with the truncated response? It's a little bit hard to tell from this data if, you know, which one of those is maybe the dominant factor. I do have this graph which shows the percent of truncated responses before, during, and after each algorithm, or this is for .com, but before the algorithm rollover. The purple line, which is in the middle here, shows the before state. That's with RSA algorithm, and then the green line, which, you know, rises up a little bit above the purple, shows the distribution when it's double signed, and then blue shows at the end when everything's better. So this obviously shows that we got a lot more truncated responses, which we already kind of know, but this is the graph that I'm sort of most interested to share, which is kind of busy and exciting here. So in this plot, each dot is one resolver IP address, and this is a scatter plot. So each axis is a percentage. This is the percentage of responses that are truncated before and during the algorithm rollover. The dots are colored by their query volume, so going from purple, blue, green, red, and so on. And kind of what we'd really like to see is we'd like to see things stay the same from before to during the rollover. We'd like to see them on the x equals y axis. That would be ideal. That would mean that each resolver had about the same amount of truncation before and after, but that's not quite what happens. There's a lot of these resolvers, especially that are colored yellow in the sort of middle range, that shifted up during the double signing period. They had a lot more truncation than they did before. There's also some very high volume sources here. Some of them you can see in red. There's even some that are, I think, colored black, which there's really too few of them to see. But, you know, they also shifted way over. So many resolvers don't fall back to TCP for truncation, either because they have no path for DNS over TCP, or maybe they're not really what we consider full service resolvers. Some of them retry very aggressively, as we saw in the case of Akamai, and we also saw here during the rollover. The double signing rollover, however, had really sort of minimal impact to resolution of existing names. It was really only the NX domain, the non-existent names, where we saw that the retry and aggressive behavior and potential problems. And I am out of time, according to the timekeeper, so there's still time for questions, though, yeah? Okay.
Jeff Houston, a really quick question on slide 20. Could you explain why in the first few, is it hours or days, there was a correlation between handing a truncated UDP response and seeing TCP? And I would say it looks like eyeballing about 60%. Then all of a sudden, the truncation rate in UDP just rises to the ceiling, but your TCP rate stays a lot lower. In other words, proportionately, it just sinks. It's almost as if at that point, a different class of resolvers is handing you the question. Can you explain that?
Yeah,
gap?
so what's going on here, Jeff, is that we add signatures to 25% of the zone per day. And so sort of in the middle is the point where we've reached some critical record, like the NSR set all of a sudden got bigger. So at the start, where they're sort of close together, the responses the responses don't go from small to big on average, right? They go from small to a little bit bigger to a little bit bigger to a little bit bigger to big over the course of 4 days. So that's why it takes a while for the UDP truncation to ramp all the way up, if that makes sense.
Doesn't make sense to me, but we'll deal with it later.
Well, I can show you offline
Sure.
and show you some other graphs that maybe represent this better than this does here.
Thank you.
Wes Herdick again. Did you consider going no? So putting on, my RSO hat this time, is there any lessons learned that you guys would have changed? Right? Is there any takeaways from this that you could give advice to future, institutions that might be rolling their algorithm at some point soon? Just thinking randomly.
Yeah, I don't think we would have changed anything. I think we're very happy with the way it turned out. For the root zone, which I think you're kind of alluding to, there's a couple of options to consider. One is we could, so the root zone uses RSA, but it uses a 2048-bit zone signing key. Previously used a smaller one. We could consider temporarily, reducing that key size again, and that would mitigate some of these concerns for the root zone. The other possibility for the root zone is, as Christian was just talking about, maybe we get to the point where the rules for multiple algorithms are not as strict, and the root zone might not have to do double signing. It might be able to do, a single sign algorithm rollover. So that would also work. Other than that, I don't have any recommendations. All right, thank you.